So we finished our talk about the different ways an airside system can be put together. And now we're going to circle back and look at some specific issues that could be associated with those airside systems, starting with our coils. So we talked in general about heat exchangers, a little bit about their arrangement, and now we want to kind of get into more of an operational issue that we might see. So this could be a typical coil arrangement that we may see, where it appears that we have a heating coil followed immediately by a cooling coil in our supply side of the air handling unit. So not only do we have this propensity for simultaneous heating and cooling if the control system is not designed or being implemented correctly to limit that, but we now have this preheat coil that has a very specific job to do, and we may want to pause and think about what that job is and if this is the correct application for that type of coil. So the job of this device is to prevent freezing in the cooling coil when the cooling coil sees less than 32-degree air going across it. So you might think that there's really not a lot of places that are going to not have under 32-degree air at some point outside. But an important thing that we want to keep in mind is that we may never really see that 32-degree air in some instances. So let's, for instance, take this air handler and say that it's part of a digital control system that has a lower limit so that when zones get below 55 degrees, the unit will activate and it'll have some unoccupied heating mode. So at the lowest case, we would expect about 55-degree air to be coming from the return. And maybe say when that happens, let's say we happen to be at our design low. In this case, we'll throw out a number for somewhere like Central California at about 38 degrees outside. So we would hope that in that unoccupied mode that our outside air damper stays closed, because we don't need ventilation, we just need airflow to accommodate that heating of the zones. But let's say our control system had some flaw and that wasn't checked, or for some reason that damper stayed open, let's call it 50% open, so it thinks it needs to meet some design ventilation, and we're actually mixing that air together. So we're still not near that 38-degree peak or anywhere near freezing. Now we're at 46 degrees because of that conservation of mass between the return air and the outside air. So we want to think in those terms because now we have a situation where we would suspect that the cooling coil would never really see freezing conditions in this application. And we've just introduced a pressure drop for the life of this air handler that can never be removed and serves no value. So we can actually take the pressure drop across that air coil and plug that into our fan equation to try and find out how much we're paying for that coil. So even if you valve it off, you might have a couple $100 or even a few $1,000, depending on the size of your fan system, associated with the pressure drop of that preheat coil. So there may be conditions where you expect stratified air and you're worried about one corner of your cooling coil being in a freezing condition, but we just really want to think about the purpose of these devices in our system, what job they're doing, and what the cost is associated with that job. And we may want to undergo that same thought experiment with our air filters. So it's another device that has a pressure drop associated with it and really is something that we can't bypass, so it's going to be with our system whenever it's in operation. So on the whole building design guide, our unified facility criteria mandates specific MERV ratings associated with our filters. So remember that MERV rating is tied to the particle size that can make it through those filters. So it's a pretty aggressive target that's in the UFC, and that's really good air filtration. But what we have to understand is that there's a cost associated with that, where we are able to catch those finer particles. We have a higher pressure drop associated with them. So there's a pre-filter that's designed to keep that final filter from loading up too quickly. So the pre-filter is this pleated type that you might see similar to your residential furnace maybe at home. And it's going to catch some of the bigger particles before it goes to this extended surface type final filter, which could be a cartridge or a bag type. And because of the fine capture capabilities of those, we're going to have a pressure drop associated with it that we could attribute a cost to. So if we look at it this way, we can understand that there's some competing interests that we have. On the one hand, we may want to delay buying new filters as long as possible to reduce our overall expenditure for buying filters. But on the other hand, the longer that we wait, the more these filters load up, and the higher pressure drop we have associated with them that translates into more fan energy. So in theory, there's some spot right in the middle, some sweet spot that we would call the optimized replacement time, where you're not doing it too soon and you're keeping your filter purchase costs low, but you're not doing it too late that you have loaded up filters that have a high pressure drop associated with them. And what's really nice is that we have automation systems that could inform us where we can get close to that sweet spot, and ideally change the way that we schedule those filter replacements. So there's a lot with airside systems that we can do when we have control systems that can not only give us data like that with the filters, but can communicate between systems. And this is particularly true when we have zone equipment talking to plant equipment. So as an example, here's a trend of duct static pressure in a specific system. So what you'll notice is that a lot of times designers will select something like 1.5 inch duct static pressure to be maintained 2/3 down the duct at all times. But that's really a design figure, the 1.5 inch. And you see a lot of systems that will maintain that design number at all times, despite the low load conditions it may be in. So what does that look like? Well, whenever you're at a condition where you're below that design cooling mode, which by definition will be most times, what may happen is most of your dampers may start constricting down. So inside the VAV boxes, the dampers will start closing because they're going to be happy and they don't necessarily need their design cooling CFM at all times. And there's a very specific system curve associated with all of that damper position and the pressure drop associated with that. So wouldn't it be nice when we're in that situation where we don't need that design level 1.5 inch of duct static, and we can lower that to say 1.25 inches, or maybe all the way down to 1 inch. And when our boxes tell us we're happy, we can hold that lower duct static pressure set point. And looking at something like the fan curve, we can see that it's possible with that less steep system curve that we can meet the airflow we need through our boxes at that reduced pressure. And then if we get to the point where one of our boxes gets starved and opens all the way, well, then we can bump our system back up. But at least this way we have a way to better meet the load in non-design conditions. And this can extend to a couple different applications. So let's say that we have dissimilar spaces that have different schedules in our building. So we might call this opportunity zone scheduling. And in this application, if we have classrooms and offices, and they both start at 7 a.m., but the offices go to 5 p.m. to where the classrooms empty at 3 p.m., well, one of the options that we have is to tell the automation system to put special schedules in the classroom zone equipment to close or mostly close those dampers starting at 3 p.m. So what we've done now is just found a way to ride our system curve down, get those CFM level savings that would translate to fan savings, and have a cube relationship with brake horsepower. What would be even better is if we could be confident that that 3 p.m. shutdown was okay because we had occupant instruction to hit a zone override. If there happens to be a study hall or someone in that space after 3 p.m., it can open that box on a local override for some bypass time, i.e. 2 hours. And then that way you're still accomplishing most of your savings, but you can keep those special instance zones happy. So automation really supports this type of zone scheduling. And we can even look at how that may affect not just how we stage the shutdown of our system, but how we start it up in the first place. So if this is a trend of outside air versus return air in a system looking over a couple days, what might we be able to tell about the way we're starting this system up? Well, one of the things that you may notice is that there's just a slight amount of drift when the system is unoccupied. And then when the fan starts up, we can see that we very quickly not only reach what looks like our set point, but overshoot it. So what might this be a sign of? Well, it looks like we have a tight building due to the slight drift, if this is an average condition that we see outside. And it looks like our system's able to very quickly warm up the spaces. So what if we had a typical 1 hour warm-up time associated with this system? Well, that might be an opportunity to use building automation data like this to trim that schedule down, or maybe even have it automatically reset to only have the warm-up time needed based on some zone temperature, how far that drifts, or how cold it is outside. So when we talk about fan savings, we have to realize that, like with the pumping systems we looked at, there's specific fan performance curves associated with different fan wheel geometry and blade type, but that we're still subject to these affinity laws for these types of dynamic devices. So when we talk about things like removing a pressure drop or limiting CFM when we don't need it, that translates into square and cube relationship savings with things like fan brake horsepower. So one more example on that point is system effect. We talked about with pumping systems how the system curve represents the summation of all the pressure drops in your most pressure drop intensive run in your pumping system. And it's the same with fan systems, except that we may want to note, because of the low pressures involved, it's easier to have a disruption and create a pressure drop in a fan system. And that can be particularly problematic when we look at the discharge of a fan. So let's say that we had this type of design that we were expecting in a new building or a retrofit. And let's say that this design was installed like this. Well, this may not be something that occupants are going to complain about, but we've now introduced a pressure drop where the fan pressure is highest that we can really never get away from. It may be too expensive to fix, but something that could have been caught during the installation. And once we start recognizing these type of opportunities, we may even have gone back to that design and told our team or instructed the contractor that we really want a system like this, rather than horizontally discharging into an open plenum, having a reducer fitting, and then ultimately what ended up being this square fitting and this backward curve that has a high pressure drop associated with the large inches of water column being put out by this fan discharge. Why not vertically discharge straight up and reduce those high pressure drops? So that's the great thing about this type of exercise, is when we start getting more into retrocommissioning scoping, we're going to see that things we find in the field are really going to inform our commissioning expertise and also what we can catch in design. So there's one usual suspect that's conspicuously missing from this conversation, and that's economizers. So this is such a criminal offender in airside system performance that we decided to make our own video about it. So we're going to get into that coming up next.